A very good day to everyone. Today we're going to be talking about the reactions of carbohydrates. Now I have a question for all of you guys. Ever wondered what really goes inside your bread? Well, I'm not talking about the bread itself. Rather, I'm talking about the sugars. Well, carbohydrates to be exact. Why don't we have a quick review on what we have learned in our previous lessons? Hopefully you guys remembered that carbohydrates are organic compounds composed of carbon, hydrogen, and oxygen atoms in a specific ratio. They serve as primary source of energy for living organisms and play essential structural roles in our cells and tissues. Let's now formally start our discussion on reactions of carbohydrates by visiting our learning outcomes. So, by the end of the lesson, the student will be able to 1. Identify and differentiate the reactions of carbohydrates. 2. Illustrate the different chemical structures of the chemical compounds involved. 3. Perform and observe the different reactions of carbohydrates. And lastly, of course, apply the importance of the reactions of carbohydrates in our everyday lives. So, before we start our discussion, why don't we have a few drills that will get our memory revved and started? All you have to do is identify a sugar group that you think will match the given sugars based on the isomer. So, are you ready? Alright, why don't we go off with D-glucose? What would be its ethane? 5, 4, 3, 2, 1. If you answer D-galactose or D-mannose, then boom, you are correct. How about we go with D-idose? What would be its enantiomer? 3, 2, 1. This is very simple. If you got L-idose, then yes, you are right again. Good job, everyone. Hopefully that revved up your memory. Let us start with our discussion. So the first reaction of carbohydrates that we'll be tackling is osazone formation. But what does this reaction entail? We'll take a look at this crystal. This is probably familiar to you as you performed this already in the laboratory. Osazone formation is a reaction that occurs in reducing sugars that contain a potentially free aldehyde or ketone group. As you can see, a condensation reaction is involved, and the end product would be the formation of osazones. These can easily be identified when viewed under a microscope. We know that this reaction is seen in reducing sugars. What are some examples of these? In what sugars can osazones form in? You can pause the video for you to think about it. Some examples include glucose, galactose, fructose, lactose, ribose, xylose, mannose, among others. Amazing work if you got all of them. Now moving on, how do we properly conduct a test for osazone formation? Well, the reagents to be used here are phenylhydrazine and acetate buffer. This includes phenylhydrazine mixture, which is composed of 2 parts phenylhydrazine, hydrochloride, and 3 parts sodium acetate, and glacial acetic acid. Glacial meaning anhydrous or free of water. Hence why this test is also termed as phenylhydrazine test. Now this right here is a general equation involving the reaction. It's fairly simple, but let's go through it together one by one. As you can see at the bottom, there are 3 stages to the chemical reaction. The reducing sugar involved, the addition of phenylhydrazine, and the formation of the osazone or phenylosazone along with its final products, aniline and ammonia. First, there is a reducing sugar to test the formation of the crystals. In our example, of course, this would be the general formula for an aldose. Next, the reducing sugar and 3 molecules of phenylhydrazine are mixed. Take note of the formula of phenylhydrazine, C6H5NH&H2. In the product side of the equation, you can see the formula of the phenylosazone. The other products that form are aniline, C6H5NH2, ammonia, NH3, and water. Simple as that. To see the equation, let's do some practice. Try it for yourself on a piece of paper and draw the structure and write the name of the phenylosazone that would form from the addition of phenylhydrazine to D-fructose sugar. You can pause the video if you still need more time. Let's check your answer. Here is a formula of fructoosazone. Did you get it right? Great job! I'm mentioning osazones a lot, and you may be wondering, what are they? Let's take a look now at the actual osazones and talk about their properties. Osazones are yellow crystalline compounds having characteristic forms and different melting points. These are easily prepared and identifiable through a microscope. As you can see from the pictures, these are what different osazones look like from various sugars. Glucosazone from glucose, fructosazone from fructose, maltosazone from maltose, and lactosazone from lactose. It can be used to differentiate sugars based on their distinctive crystalline structures. though most of them are yellow, the crystals are unique to the sugar from which they are formed, as evidenced by the pictures. They all have unique characteristics and features, although their formation process is the same. This table right here shows the properties of all four of these ozones. You can see the time it takes for these crystals to form as well as the crystalline structure's appearance. For glucosazone, it takes 5 minutes to form a needle-shaped structure. For fructosazone, it takes only 2 minutes but also forms a needle-shaped structure. Although these two have similar structures, they have different time formations. Later we'll talk about why this happens. Maltosazone and lactosazone take a bit longer to form, approximately in 30 to 45 minutes, and show a sunflower-shaped structures and powder puff-shaped structure respectively. Let me ask you this. Why would sucrose not form any ozones? We've seen lactose and maltose form ozones even though they are disaccharides, so why can't sucrose? Try to remember what we've discussed in the beginning of this reaction. Got it? This is because sucrose is a non-reducing sugar, with no free aldehyde or ketone group. As previously mentioned, ozones only occur in those sugars that are reducing and have a free aldehyde or ketone group. So why is there a picture here of sucrose with ozones? Sucrose itself won't form ozones, but its monomeric units, glucose and fructose, can. Mention that glucose and fructose form similar ozones, right? Actually, glucose, fructose, and mannose form the same ozone called glucosazone because they have identical configurations at carbons 3, 4, 5, 6, in which case identification becomes difficult. It is evident from their formulas that they are similar, and this is what their general formula would look like as phenylozazone. Let's talk about its uses and applications. Ozone formation is useful in the identification of sugars, especially reducing ones. It is actually the only one that can differentiate lactose and maltose. It can be conducted easily because it is simple, inexpensive, and time efficient. We can use this to detect sugars and plant tissues as well. And lastly, it distinguishes reducing sugars from each other and reducing from non-reducing sugars. The next type of reaction formation of carbohydrates is oxidation. So what is oxidation? Oxidation is defined as the addition of oxygen to the substance or the removal of hydrogen to the substance. For example, the corrosion of metal. Metal reacts with its environment to form a more stable compound, typically an oxide, hydroxide, or sulfide. This process results in the deterioration of the metal's properties and appearance. Metals typically corrode when exposed to environments containing oxygen and moisture. Except sucrose, disaccharides and monosaccharides, especially the aldoses, are readily oxidized, forming sugar acids. Is sucrose not readily oxidized, forming sugar acids? Sucrose's inability to readily oxidize and form sugar acids is due to its specific structure, which lacks the free reactive groups necessary for oxidation. The glycosidic bond between the glucose and fructose units effectively prevents sucrose from participating in oxidation reactions under mild conditions, classifying it as a non-reducing sugar. Reaction begins at the aldehyde group, then the primary alcohol, and lastly the secondary alcohol. There are three types of acids that will form oxidation reactions: aldonic acid, aldaric acid, and lastly, uronic acid. Aldonic acid, formed by the oxidation of the aldehyde group, which is CHO, of an aldose sugar to a carboxylic acid group, COOH. When the aldehyde group of an aldose is oxidized, a so-called aldonic acid is formed. In naming an aldonic acid, the suffix "-ose" is replaced by onic acid. D-glucose is oxidized at its aldehyde group to form D-gluconate. Next type of reaction is aldaric acid, formed by the oxidation of both the aldehyde group CHO and primary alcohol group CH2OH, and of the aldose sugar to carboxylic acid groups COOH. If both ends of an aldose chain are oxidized to carboxylic acids, the product is called an aldaric acid. In naming an aldaric acid, the suffix "-ose" of the systemic name or trivial name is changed into aric acid. D-glucose is treated with nitric acid HNO3. Both the aldehyde group at carbon 1 and the primary alcohol group at carbon 6 are oxidized to carboxylic acid groups. This converts D-glucose into glucaric acid with carboxylic acid groups at both ends of the molecule. Last type of acid is uronic acid, formed by the oxidation of the primary alcohol group at the end of an aldose sugar to a carboxylic acid group, while the aldehyde group remains unchanged. The hydroxyl group, furthest from the carbonyl group, has been oxidized to a carboxylic acid. These compounds are named by substituting "-ose" with uronic acid. D-glucose is treated with mild oxidizing agent. the primary alcohol group at carbon 6 is selectively oxidized to a carboxylic acid group, forming D-glucuronic acid, which leaving the aldehyde group at carbon 1 unchanged. What role does glucuronic acid play in our body's physiology? It's the formation of cartilage and acts as a detoxifying agent within the body by binding to harmful substances, which are then excreted through urine. Now moving on to our next reaction. Have you ever wondered how rusty clocks can be converted back to their shiny selves? Well, that is due to the reduction reaction. The reduction reaction is a chemical reaction that involves the gaining of electrons by a molecule, atom, or ion. It is the exact opposite of oxidation, which explains why it can reverse the process of rusting. I hope you remember that all monosaccharides and disaccharides that contain a free aldehyde and ketone group can actually reduce other substances, aside from sucrose. Again, sucrose is a disaccharide that does not have a free aldehyde or ketone group, as you can observe in the image. The reduction can be identified in different ways. It can be gaining of electrons, the decrease in oxidation state, the gaining of hydrogen, and the loss of oxygen. But how do all of these work? Well, first of all, the gaining of electrons, as you can see here, is very simple. When adding an electron to a specific substance, it can cause its state to be negative. Well, this is because when an atom gains one or more electrons, it acquires a greater number of negative charges than positive charges, which we call protons. This imbalance results in a net negative charge, and the atom becomes negatively charged ion, known as an ion. This is the decrease in the oxidation state. Here's an example of copper ion having an oxidation state of positive 2, being added with 2 electrons. Since the copper ion has a positive 2 charge, it already has a reserve for the electron when added, leading to a product that cancels out both the negatively charged electron and positive charged copper ion, leading to metallic copper in its neutral state. Second to the last is the gaining of hydrogen, which is very common for carbohydrates. Here we have glucose, which is a simple sugar, going through a process called hydrogenation, where a specific substance is being added with hydrogen, and in this case, added with 2 hydrogen molecules, reducing it to allyl, which is the product in this reaction. And lastly, we have the loss of oxygen. This type of process requires a reducing agent, and in this example, we have carbon monoxide as our reducing agent. So as you can see in the example, ferric oxide gets its oxygen taken away by the reducing agent through the process of elimination, turning the ferric oxide to iron. See? Wasn't that so easy? Now in the next following slides, I'll show you how sugars can be reduced with the use of catalysts. As an active recall, catalysts are substances that help in the chemical reaction without being consumed and altered. Now in the first example, you can see here that ribose is being reduced to xylitol with the use of xylose reductase as the catalyst, which is considered as an enzyme. And in the second example, glucose is being reduced to sorbitol through an acid catalyst. So this time, we are using a base as our catalyst. Here we have sodium borohydride helping in the reduction process of glucose, reducing it to sorbitol. And lastly, the utilization of metal catalysts, such as nickel here, reducing glucose to sorbitol. But did you know, sugars can actually be used as reducing agents as well? Carbohydrates that contain free aldehyde or ketone group have the ability to reduce. There are 2 types of carbohydrates that can be reducing agents. That would be the monosaccharides and disaccharides. Monosaccharides are simple sugars that contain only 1 pyranose ring. This is where the mono came from. Examples of the sugars are glucose, fructose, and lactose. Here in the example, we are using glucose in its aqueous solution to reduce the copper ion. Yes! We are almost done with the reduction reaction. In this slide, the disaccharide, unlike monosaccharide, contains 2 pyranose rings. Hence, it is called di. Hopefully you remember the fun fact earlier about sucrose not being a reducing agent despite being a disaccharide. Do you remember why? That's right, because it does not contain a free aldehyde or ketone group. So in this example, same as earlier, we have a sugar that is used as a reducing agent to reduce the copper ion to metallic copper in its neutral state. Always remember guys, if you have any clarifications or questions, don't hesitate to message me via Teams and I'll do my best to answer any of your questions. Okay, now let's find out if you really did listen to this discussion. The first 10 students to type the answer on the comments will have a 5 additional points for the next long exam. So, can you give me examples of catalysts that help in the reduction process of carbohydrates? You have now reached a checkpoint in our discussion. It's time for recall. Why don't we play a game called Guess the Reaction? A slide will display a chemical equation and you need to identify it. If you don't get it right, you'll have to do a dare. I wonder what kind of reaction is this? If you answered ozone formation, then yes, you are correct. However, if you answered wrong, womp womp, your consequence is impersonate a famous Filipino celebrity. Next, we have this. The answer, drumroll please, it's oxidation. Once again, if you answered wrong, you must explain what you have learned so far in Tagalog. Nako, mahirap ba itong ipapaliwanag sa Tagalog? Aabangan. Sa wakas, ano kaya ito? Finally, our last equation before we proceed to the second half of our discussion. It was reduction! Congratulations to everyone who got it correct. Yay! However, if you got it wrong, here is our final consequence of the day. You have to sing a verse from a Bini song of your choice. Eh, kamuna, eh! Well done, everyone. Let's now proceed to the second portion of our discussion. Remember when I said what goes inside your bread? We will now be finding out what happens to sugar that undergo alcoholic fermentation. Alcoholic fermentation is the process of decomposition of carbohydrates due to the action of microorganisms such as yeast, molds, and bacteria. Sugar used to make bread is converted to ethanol and carbon dioxide, which fills the dough and increases its volume. What are some other practical uses of alcohol fermentation? If beverage production, such as beer and wine, along with bread making, crosses your mind, then that's correct. Here's an important fact to know. Yeast only ferments the naturally occurring D-glucose, D-mannose, and D-fructose. If ever you have any clarifications or questions whatsoever, don't hesitate to message me via Teams. Now we move on to amino sugars. But before that, I would like to ask you if you're familiar with aldohexoses. Aldo and word hexose. It is a sugar with 6 carbons and an aldehyde functional group, hence the hexagonal structure. In this graphic, we can see that when the hydroxyl group of the second carbon in the aldohexose is being replaced with an amide group, an amino sugar is formed. In this case, an alpha-D-glucopyranose becomes an alpha-D-glucosamine. The 3 amino sugars that can be found naturally are D-glucosamine, D-galactosamine, and D-manosamine. From what we learned about amino sugars so far, what do you think their functions are? Well, amino sugars are essential parts of the molecule of microsubstances. They function primarily as a blood anticoagulant, as a blood component, as an energy source, and as a ground substance of connective tissues. Go through them one by one. Amino sugars serve as an anticoagulant because they prevent blood clotting by inhibiting clotting factors. Amino sugars are blood components because they are integral components of glycoproteins and glycolipids. They are energy sources because they are involved in the metabolic pathways that provide energy. Lastly, they serve as a ground substances in connective tissues as they are fundamental components of the extracellular matrix or ECM, providing structural support and elasticity. Some examples of amino sugars are heparin, which is a naturally occurring anticoagulant, streptomycin, which is an antibiotic used to treat bacterial infections like tuberculosis, puromycin, which is an antibiotic that inhibits protein, and glucosamine, which is the building block for glycosaminoglycans, a crucial part of connective tissues. Now let's talk about esterification. To recall, esterification is the process of combining an organic acid with an alcohol. This reaction forms an ester bond and water. In the case of carbohydrates, the acid that reacts with the alcohol group is typically a phosphoric acid. As just mentioned, esterification is the reaction between an alcohol and an acid. The reason this reaction occurs in sugars is because of the presence of the primary alcohol group. Here is an example of esterification with carboxylic acid and an alcohol. The reaction of these two functional groups form an ester. In biological systems, carbohydrate esterification is catalyzed through enzymes. Some enzymes that do this are lipases, esterases, acyltransferases, carboxylesterases, alcohol dehydrogenases, and acyl-CoA synthetase. It's very hard to say all of these at once. So here is an example. As you can see, the hydroxyl group on the 6th carbon of glucose reacts with the phosphate group from ATP, forming glucose 6-phosphate. This process is catalyzed by hexokinase. Now let us head to the last kind of reaction for carbohydrate, reaction of alkali. In this reaction, a process of interconversion occurs between 3 different monosaccharides, which are glucose, fructose, and mannose. So class, I want to ask, what happens when one of these are allowed to stand for some time in the presence of a weak alkali? Does anyone have a clue? When any of the 3 monosaccharides are allowed to stand in the presence of a weak alkali, like barium borohydride, it is converted into a mixture containing glucose, fructose, and mannose. Furthermore, whichever one of the 3 is used initially, the same proportion of the 3 sugars is always reached at equilibrium. Isn't that fascinating? Before we proceed, does anyone of the class knows how the transformation of the reaction occurs? Well, in the action of alkali, certain steps of the transformation occur. To begin, there is a rearrangement of the radicals in the first 2 carbon atoms. Afterwards, there is a formation of an intermediate enol. Lastly, any one of the 3 sugars can readily be formed. Should we understand the transformation, let's have some examples. Here, we have a D-glucose. We first begin with an introduction of an OH molecule, which attracts the H atom of the 2nd carbon atom. Then, we produce an enol. However, due to the loss of an H atom, the 2nd carbon atom would bear a negative charge. And with this negative charge, it would cause a chain of reaction wherein there would be a loss of double bond on first carbon and an attraction of another H2O molecule from the outside environment. Afterwards, all of these chain of reaction would further transform D-glucose into D-mannose. Next, we have another example of D-glucose transformation. However, in this case, we have a presence of both an acid and a base. The base molecule attracts the H atom of the 2nd carbon atom, whereas the acid molecule attracts the H of the OH atom attached to the 1st carbon atom. This results into a chain of reaction wherein there is a development of a double bond due to the electronegativity that is developed by the 2nd carbon due to the loss of its attached H atom, produce an enediol and then further transform into D-fructose. More generalized process of how a D-fructose creates an enediol due to the presence of an OH or base, which would then further convert into either D-glucose or D-mannose. Do you notice how the arrows are both point at 2 different directions? This means that the reaction is reversible and can go to either formation, which proves that if either of the 3 sugars are placed in a basic environment, it can produce into either of the 3 sugars. Now, does any of the class know the importance of this phenomenon in our body? Well, our body is capable of converting simple sugars into another, like how utilizable sugars are converted into D-glucose and its continuous conversion into D-fructose and D-mannose. This interconversion ensures that the body has a consistent supply of necessary sugars that can be utilized in different necessary processes like metabolism. So did anyone feel amazed by that? Does anyone have any questions whatsoever? Well, if none, that would be all for the reactions of alkali. Have a short interactive board exercise. Let's go back to the question I asked at the beginning of my presentation. How does yeast work in the workings of bread making?
Understanding how bread's ingredients work can take the stress out of baking. The most unfamiliar ingredient you'll see in any bread recipe is yeast. Yeast is a living, single-celled organism that causes dough to rise. Dough must rise in order to have the fluffy quality people expect in bread. Here's how yeast works. Any recipe that calls for a packet of dry active yeast will also include about a tablespoon of sugar and warm water. Every packet of yeast contains hundreds of billions of living yeast cells that have to be activated. Think of it as billions of teeny tiny sleeping monsters. You wake up these monsters by throwing them into warm water. The water can't be too cold or it won't wake them up, but it can't be too hot, you'll boil them to death. Once you wake up the yeast, the tiny monsters start gobbling up that spoonful of sugar. When they eat the sugar, they burp up carbon dioxide, CO2. This process is called fermentation. Take a look at the yeast now. You see all that foam? What you're seeing is the CO2. After I wake up the yeast, I add in the binding ingredients: oil, sugar, and eggs. These ingredients help keep everything together and add flavor.
You have now reached the end of our lesson. Your learning outcomes have been achieved, and it is now time for a short evaluation. At this juncture, 5 multiple choice questions will be shown on the screen, and please submit your answers on the comments section below. My name is Karian Dibaligwa, your teacher for today.